The climate is clearly changing. We all see that. We can all perceive that. Conditions here are dramatically different than they were just, say, 20 years ago. Our human response to air pollution is pretty acute. If you are susceptible to have health effects from air pollution, it's going to happen right away. You also have this confounding problem from agricultural burning in the extreme Northwest. Both in India and Pakistan, air quality does not know any boundaries. It does not restrict itself to a particular geographic boundary. It does not have a passport. It goes wherever it wants to go.
What would an ideal policy look like for a country like ours?
All we can be sure of is that things are changing, and it's because of the things that we put into the atmosphere.
The winter months in India are around the corner, and words like air pollution, AQI, smog, and crop burning will begin to re enter our vocabulary. But what do these words really mean, and how do these tiny, invisible particles in the air shape our health and the climate we live in? Welcome to the Boring Climate Podcast, a platform where we encourage serious climate conversations. Today, we're joined by Dr. Richard Peltier, an expert in environmental health and one of the world's top minds on atmospheric aerosols. Dr. Peltier is a professor at the University of Massachusetts Amherst, where he leads research on air quality, aerosol chemistry, and the health impacts of air pollution. With advanced degrees in public health and environmental sciences, he has served on advisory panels of governments and global bodies, including the World Health Organization, helping set air quality standards and driving international dialogue on pollution and climate. He brings a truly holistic view, and we can't wait to start this conversation. Welcome to the show, Richard.
Oh, thanks so much for having me today. It's really great to be here.
So to start off with, we'll start with the basics. What is an aerosol, and how is it different from, say, greenhouse gases or vapors?
Sure. So aerosol is a term. It's a technical term that includes the gases and the particles in the air. It's a catch-all, and essentially anything in the atmosphere is an aerosol. But when we think about what causes health impacts on you and I, it's actually both some of the gases and some of the particles. My own research focuses on the particles, but that doesn't mean that the gases aren't important either. Climate change is a little bit different. They're both impacted. Both climate and health are impacted by aerosols, but through different ways. The climate is impacted by aerosols because aerosols make climate get worse. It can make the presence of little particles in the atmosphere can create clouds, which reflect sun, which decreases the amount of heat that reaches the earth. And other kinds of gases that are in the atmosphere capture some of that heat. So these are old science stories that we've been talking about for a long time. Aerosols are important for both health and climate, but for very different reasons.
Which was actually my next question. How are they important for health and climate, if we were to break it down for the uninitiated?
Sure. So we'll split the question into two. When we talk about health, and that's my own area of focus, we look at how the materials that are in the atmosphere, so the particles and the gases and little droplets floating around that you can sometimes see, they get into our bodies typically through breathing. When we take a deep breath, the particles and gases enter into our lungs, where they impact us both at the site of ingestion, where they come into our bodies, but also they spread around our bodies everywhere. When we breathe in and breathe particles in, those particles impact our lungs, but they also get into our bloodstream and affect our brains and our hearts, and they cause cancer and all sorts of different things. And so what we're most interested in the health world is figuring out which sources of air pollution are the most impactful to health. Climate is a different side of the same coin. Climate, of course, is more of a long-term implication for the world. As we put more carbon into the atmosphere, that carbon has been able to retain and hold on to more of that heat in the atmosphere, causing our climate typically to warm. That's not always true. It's really just changing. And at the same time, it's very complicated because the presence of air pollution both causes climate change to get worse, and in some cases, it actually improves climate change. The presence of small droplets form clouds, which actually lower the amount of heat that reaches the earth. So it's a balance. On balance or on whole, we've been kind of losing here, where the climate is clearly changing. We all see that. We can all perceive that. Even where I live in the eastern part of the United States, the conditions here are dramatically different than they were just, say, 20 years ago. And that's largely driven by climatic changes that have been occurring really since the 1910s and 1920s with the introduction of these materials in the atmosphere. So Air pollution and aerosols are important for both health and climate, but for very different reasons. But both of them are really, but aerosols are really important to understand and control because if you can do that, you can get a better handle on reducing health effects in people, but also improving our climate.
Right. So we'll kind of zoom into the climate aspect first. In terms of predicting our changing climate and, say, extreme weather events, how hard is it to understand the role that aerosols play compared to other known sources like greenhouse gas emissions?
Sure. Let's go to the easier one, greenhouse gas emissions, and let's just simplify it even further and only talk about carbon dioxide. There are many greenhouse gases that are out there, but if we just talk about carbon dioxide, we have a pretty good understanding of for every ton of carbon dioxide you put in the atmosphere, it's going to result in a certain amount of heating or heating potential. That's a pretty well known and well characterized fact. When you get into something like aerosols, it's very uncertain. And what I mean by that is that we think something's going to happen in a certain way, but we're not 100% sure of it. And aerosols are really, really complicated because they have this two-sided effect. In some contexts, the aerosols make climate change worse, and in other contexts, climate change is improved. A simple example of that are two different kinds of particles that are pretty common in the atmosphere. One is known as black carbon, and it's the black material that you see coming out of a diesel engine, for example. It's that sooty stuff. Black carbon is, of course, dark in color and absorbs a lot of heat, especially when that black carbon lands on, say, a glacier, because you're changing the natural color of that glacier from white to a darker color. And in doing so, you're going to attract more heat. Anybody who's walked on pavement in the summertime knows that that asphalt heats up very, very hot. The same kind of principle happens with the deposition of black carbon on a surface. But another kind of particle, say ammonium sulfate, which is a chemical, it's a salt that has the potential to form these little tiny cloud droplets in the atmosphere. And if you can form more cloud droplets in the atmosphere, you can reflect more sunlight. And so that has a net cooling effect. And so aerosols do both. They make climate worse and they make climate better. And so finding out what the balance is, the net effect, is really tricky. And it really does depend on the mixture of different kinds of pollutants in a certain area, where and when those pollutants occur and where they go. And so that's where it gets really, really uncertain. We think on the whole that aerosols contribute to a small amount of global warming. The planet is warming because of aerosols. It's a relatively small fraction compared to all of the greenhouse gases that are emitted. And those greenhouse gases are something we know a lot more about and we're much more precise and sure about. So my point here is we know a lot about climate change. We know a lot of why it happens, but there's still a lot of uncertainty with things like aerosols and whether they are the worst thing in the world for us or not so bad. My personal viewpoint, based on what I see in the literature, is that they are an important part of climate change, and that on the whole they are driving climate change. But if you want to spend a dollar or a rupee to fix climate change, you're probably better off reducing carbon than reducing particles. However, a big caveat, and I say this as a completely biased health researcher, you get more benefit from reducing aerosols because not only can improve climate but can also improve health, and those health effects occur very, very quickly. We're talking, within a year of being able to reduce aerosols. That's my own personal bias. I know that's not always the way you want to foresee the world, but I think if you're looking for a solution to improve climate and reduce this change that we're seeing, you're going to have to go after greenhouse gases first.
Right. So the way I understand it is it's not as simple as saying we reduce aerosols in the atmosphere and improve our air quality, and automatically we've solved one of the aggressors of one of the causes of climate change. But it depends on the sources of these aerosols, right? So where do these emissions come from?
Yeah, so the aerosols, whether they're driving climate or driving health effects, come from all sorts of different places. We think of them in two broad categories. One is known as a primary particle or primary aerosol, and another is a secondary aerosol. A primary aerosol is something that comes right out of a combustion tailpipe and exhaust pipe from an engine, like a car or a truck, or from a factory, and those are the particles that you can often see in the atmosphere. But then at the same time, often mixed within those particles are all these gases that you can't see. They're invisible. You can't really detect them very easily. And those gases will float around in the atmosphere over time, and they'll form particles later. They interact with each other, and chemistry happens in the atmosphere, and they form additional particles. And those are known as secondary aerosols. Those are secondary particles. They form after the fact. And it's one of the reasons why, say, if you were to look at, say, a power plant emission, if you were to measure the number of particles coming out of a power plant emission or very close to a power plant facility, you wouldn't see a whole lot of particles. Why? Because they're mostly in the gas phase. They're not yet a particle. They're floating around as vapors, and then over a few hours or sometimes a few days, those vapors will condense together and they'll bang into each other and they'll stick and they'll form this big droplet. And that we call that's a particle as well. That process takes hours to days for it to form. And so that power plant may not be impacting the immediate surrounding community, but it will well downwind to that community.
Some of these terms that are kind of loosely thrown around, ambient air quality, fugitive air emissions. What do these mean in your research, and how can we better understand what they are?
Sure. That's one of the hard parts of doing what we do is we use some technical words and jargon that a lot of people don't understand. And it makes it more efficient for a researcher like me to be able to communicate results and talk to my colleagues and do good science. But it's hard to make that message reachable to the broader public. And it's important to be able to define those terms in ways that people understand. So when we talk about things like ambient air pollution is typically the pollution that's outside, that's on the street, that's in your community, in your neighborhood. It's the material that's floating in the atmosphere that goes wherever it wants to go, wherever the wind happens to send it. And that's important for a few reasons. One is that when we talk about measurements of air pollution, whether it's a government or often an academic investigator, what we're measuring is ambient air pollution. We have a monitor that's set up somewhere and it's sampling outdoor air. Uh, and that's typically how the regulatory framework is designed so that the monitors are sampling ambient air pollution. But there's a problem with that. While it's convenient to set up a laboratory to measure ambient air pollution for a government, the problem is you and I don't spend all of our time outdoors. We spend roughly 80 or 90% of our time indoors in our offices and our homes. And that's where these exposures to air pollution are also important. But at the same time, it's really hard to make a measurement of what's happening in your home or my home or somebody else's home because our activities are so different and so diverse. Some people cook a lot, some people don't. Some people have carpeting, some people have wood or tile. All of these things influence indoor air quality. And so when we talk about the difference between ambient air quality, that's outdoors, and indoor air quality, indoor is just what's happening in the indoor environment. It's important, but we know very little about it. There are lots of research studies that have looked at individual homes or communities and characterized what's happening in an indoor environment. But that's not really generalizable. What I mean by that is that the results from my house may not be applicable to your house. And so as a result, we don't really know what your exposure is going to look like. And if we really want to understand health effects, we have to understand that full environment. That your exposure is really a combination of what happens from the outdoors when you're outdoors, but also what's happening on your indoor environment as well. And that indoor environment is the one that is the most diverse and probably the most difficult to capture. Um, there are lots of other terms too that we often kind of throw around in the scientific world that I get they're confusing and complicated, like the term PM 2.5. PM 2.5 is what we call particulate matter, and it's a certain size of particles. It's the smallest particles, the ones that get into the deepest parts of your lung. We just call it PM 2.5 because for us it's efficient and convenient. But for a lot of people, that's a scary term. It's something that's not really easy to define. It's not really easy to understand what that means. And it's our responsibility as scientists to be able to explain that to the general public in ways that the public can understand. So podcasts just like this is exactly the kind of outreach that you need to have to kind of translate the results from science speak to what you might be saying with your family members or your children or your grandparents who don't have training in these fields.
Right, which was actually what I was going to ask you next. And while it's a really basic question, what is PM 2.5? What is PM 10? What is black carbon? Very briefly, if we were to break it down.
Sure. So when you look outside on a smoggy day and you see that kind of looks kind of cloudy or hazy, what you're looking at are trillions or quadrillions of little tiny particles in the atmosphere. And you're looking across the atmosphere and you're just seeing this haze of all of this light being scattered by millions and billions and trillions of little particles floating around, and they're in the atmosphere. The particles themselves are either solids, like little salt crystals, or they're droplets, like water droplets. But they're so small that you cannot see an individual particle. They're microscopic. And they come in a variety of sizes, ranging from a few nanometers, which is a billionth of a meter, all the way up to maybe 100 microns, which is much, much larger, of course. 100 microns is also nearly invisible. It's about the about 1/10 of a millimeter, something like that. And these particles are floating in the atmosphere, and they're present in a range of sizes, from nearly zero to something quite large. Uh, PM 2.5 is really all of the particles that are less than 2.5 microns in diameter. So these are tiny, tiny particles that are, again, microscopic and impossible to see. PM10 are all the particles that are less than 10 microns in diameter, so a little bit bigger. And when we talk about other terms like black carbon and elemental carbon, that's a specific kind of chemical that's in particles. And again, as I mentioned earlier, these are the black sooty materials that you see typically coming out of diesel combustion. So whether it's a power plant or a truck or a vehicle or some kind of fire that has diesel in it, that black sooty material is black carbon. It's a little bit different chemically than a generic PM 2.5 particle, but it's something that we know is important, particularly in urban environments where you have a lot of diesel combustion happening.
Right. So your studies kind of span geographies. So you've done studies in Delhi, but also in New York. Have there been any common trends that you've noticed, and any kind of surprising contradictions in what you found out when we compare just two major urban centers?
Yeah, so I think this isn't a scientific commonality, but one of the things that I often observe is a lack of knowledge about how air quality affects a community. Whether you're in New York or Delhi or Kathmandu or Ho Chi Minh, people don't recognize that this is a potential risk to them. It is something that is around you all the time. It becomes something that you are just used to. It's just part of your environment, your world. But as a scientist, I know that there's an inherent risk to having that around you. That every breath you take, and you take 20,000 breaths a day, you're going to inhale those particles, and that's going to lead to an increased risk of different health effects, whether it's cardiovascular disease or cancer. Uh, and so I think the commonality that I see across all of these diverse places that I work is that air quality is not that important to people. It's frustrating for sure. And as a scientist, I see what the science tells us, and is that there's risk to having air pollution in your community, in your homes, particularly for certain populations. I know you might want to talk about vulnerable populations later, but there are clear risks that come with having air pollution around us. And at the same time, people are not aware of those risks. People don't, it's not that they diminish the risk. It's not that they just say, oh, I don't believe you. It's that they're just not aware of it. In part because it's something that's really hard to see. It's not easy to detect air quality. It's something that takes sophisticated instruments that we have access to, but the general public usually does not. There are ways to visualize air pollution. It's not that hard to do. For example, if you have a window in your home or workplace and you run your finger along that windowsill, at the end of the day, you'll often find a smudge of dirt on your fingertip. That smudge of dirt is not dirt, that's actually air pollution that's settled on your windowsill. And so you can see it. But for most people, it's not that important. It's not something that is highly prioritized. In terms of the science of different places, the answer is that no, well, there isn't a lot of commonality across the different places because I work in so many diverse locations from very much the global south to the global north. Most of my work, I'll admit, is in the global south, where we're often dealing with orders of magnitude problems, meaning that the problems in, say, West Africa are in order of magnitude worse than they are in, say, Western United States, where air quality, we've been working on that gradually for, say, 40 or 50 years, and we've made tremendous progress over those 40 or 50 years. But these other nations are just beginning their process. They're just beginning this attempt and initiative to improve air quality. There are politics involved because air quality is intrinsically linked to politics and economics. We know that controlling air quality and improving air quality comes with a cost. Often the cost of putting in emissions controls of factories and those sorts of things. And that cost inhibits development and growth, economic growth. And so there's often a reluctance to do that. We see that in the United States too. Even now, 40 or 50 years after we've started, we still see that reluctance. We still see this political movement to free ourselves of air quality regulations because there's a burden to business. I would make a pretty strong argument that that burden to business is tiny compared to the benefit to the society when you have those air quality improvements. Uh, we've learned that lesson time and time again. And so I find that when I work in communities that are new to the air quality world, it's sometimes a tough sell to say, look, you've got these polluting factories that are emitting into your community. It's going to cost you X amount of money to improve that. But what you'll see in 2 years is an improvement in health effects in the people who live here, a decline in hospitalizations and deaths, and those have value. It's really hard to sell the potential value of you not getting sick 2 years from now from an actual cost today of, say, $1 million to put an emission control system on your factory. So it's a difficult sell. That sell was kind of forced to the United States by some federal laws. Uh, Many nations don't have those kinds of federal laws in place yet. And so I feel a little bit like Back to the Future for us, where we're going back and saying the same story we talked about 30 and 40 years ago, trying to sell the value of air quality, even though there's a cost to making those improvements today.
Right. You spoke about it being a difficult sell, and one of the things that we've started to now acknowledge is how interconnected pollution is with extreme weather events in many cases, and extreme weather events obviously leading to a lot of loss of life. Um, is aerosols linked to extreme weather events, say heavy rains or heat waves?
Yeah, so I can't give you a good, strong answer on that one. We know that aerosols are driving climate, and it's driving it in ways that we're not 100% sure. It's probably a net warming effect, but we're not 100% sure of that. We do know that the presence of aerosols form clouds more readily. You wind up getting clouds happening more frequently. And so we are seeing some changes on things like monsoons, particularly in South Asia, where you're seeing, you have a pretty regular monsoon season that's changing. We do see that happening. Uh, we don't know if that's because of aerosols that are in the atmosphere or because of sea surface temperatures or because of atmospheric temperatures that are either in the monsoon generation region or elsewhere. Our meteorology and our weather systems are global. They are connected. What happens here in the United States impacts what happens in India or anywhere in the world. And so we don't know what the mechanism is, why the monsoons are changing, why we're getting more hurricanes in the United States, why tornadoes are more impactful in the US. I live in a very I live in a part of the country where tornadoes are not something that ever happens. But we've had a couple of tornadoes in the past 5 years. As somebody who's lived in this region for almost 50 years, I've never seen tornadoes until now. And so these kinds of things are changing. We can see it anecdotally, we can see it scientifically. It probably is linked to aerosols in some way, shape, or form, but we can't be sure what that link is. All we can be sure of is that things are changing, and it's because of the things that we put into the atmosphere.
Right, so we'll move on to the health impacts. And to kind of lay the foundation, we could go back to the study you did in Kathmandu. I think you surveyed traffic police officials. Could you tell us a bit more about what you found and how those results might translate to similar cities or similar settings?
Yeah, so that study, to kind of give you a preface, we looked at traffic police officers who were working in Kathmandu. This is in 2015 and 2016, so almost 10 years ago. And these police officers were standing on the streets directing traffic. They don't have traffic lights, traditional electric traffic lights. They have humans who are directing traffic. Many of the roads themselves were not paved. There was no asphalt or bitumen on the ground, so it was gravel or dirt. And it was pretty polluted conditions. And and they're all the traffic police officers were typically young. They're in their 20s. They all have a similar background in education, so they actually were a really nice population for study because they weren't particularly diverse, which as a scientist is actually useful to us because the diversity of humanity makes it really difficult sometimes to tell the story. Anyways, This group of police officers agreed to wear scientific equipment that we could monitor aerosols. We could collect from their body with a little tube near their face, collect samples 24 hours a day for about a week. And we could every couple of days we would measure their lung function. We would check whether their lungs were working properly. We would check their cardiac activity. We had Holter monitors, which are the little EKG electrodes you wear on your chest, and a few other kinds of measurements that we had collected. Uh, Halfway through the week, we asked them to wear a respirator mask. So these are the respirator masks that not the paper surgical masks that are commonly worn, but the more form-fitting. In the United States, we call it an N95 mask. There are similar Indian standard masks. These are pretty sophisticated face masks that essentially produce outstanding protection from the atmosphere and environment. They would wear these masks for about half of the week, and then we would assess their lung function and their blood pressure and their cardiac activity. And at the time, we weren't really sure what we would find. Could a 2-day or 3-day intervention, that's what the face mask is called, have an acute benefit to the wearer of a young, healthy population? And it turns out that it did. Lung function improved even from just wearing a face mask for a couple of days. So that temporal effect, wearing a face mask for a day or two, led to health improvements in this young, healthy population from who were admittedly working in a very polluted environment. A kind of a side project to that was actually the assessment of cloth face masks. Again, this is in 2016, 2017. Many people in Nepal were wearing cloth face masks as a way to protect themselves from air pollution. People who were concerned about it, but it occurred to us that we weren't really sure if those were doing much. And so we assessed those in the laboratory to see whether they actually blocked air pollution or not. And it turns out that they really didn't. They blocked maybe 10 or 15 or 20% of the particles, but that was about it, which means that they weren't very effective. They didn't make you feel better, but they weren't doing much for air pollution. That was kind of a boring study until, of course, the pandemic hit. And then it became a much more important study because it was one of the only ones that looked at cloth face mask implements. Uh, but in terms of what the results mean, the results mean that our human response to air pollution is pretty acute. That if you are susceptible to have health effects from air pollution, it's going to happen right away, on the order of hours to days. What it also means is that there are classes of workers who are exposed to intense levels of air pollution as the nature of their job. Traffic police officers in Nepal are one example. Construction workers might be another. People who work in the outdoor environment, particularly in polluted areas, may be another. There are lots of different classes here of people who are most susceptible, most vulnerable. Uh, Ultimately, the project itself was a small scale project looking at a small group of about 60 or 70 traffic police officers. But it was enough to result in a couple of papers, publications, scientific publications, showing that the use of N95 face masks were effective at reducing ambient air pollution exposure. That's what these people were being exposed to. Uh, that being said, we recognize and acknowledge that there are limits to that because at the end of the day, nobody really wants to wear an N95 face masks. They're uncomfortable, they're awkward, and they're hard to talk, and particularly in warm environments, they're incredibly hot, and they're just uncomfortable to wear. And so it became clear that while this is a nice short-term strategy to improve health, it's not a useful long-term strategy. The long-term strategy has to come from improvements in air quality as a result of declining the emissions that are responsible for that air quality. Um, the thing about, and I guess I'll talk a little bit about health now, if that's okay.
Yes.
The thing about air pollution and health effects are that we often think that when you take a deep breath, those particles are going to impact inside your lung and they're going to cause us to have an asthma attack or make us cough or something like that. And that does happen for sure. But what also happens is changes in our body's function as a result of that exposure. And what I mean by that is one of the measurements that we collect is something known as heart rate variability. And heart rate variability, without going too far into the details, is essentially your body's ability to change your heart rate as a result of stress or metabolic change. So when you run up a flight of stairs, you want your heart rate to increase just slightly to accommodate that extra burden of running up a flight of stairs, carrying a heavy package. And so our body accommodates to that, and it adjusts the heart rate to meet the demand that you and I might have throughout our daily living. But it turns out that when you are breathing air pollution at the same time, our heart's ability to adapt to that metabolic change, that demand for a little extra pumping of your heart because you ran up a flight of stairs with a heavy bag, that ability to accommodate that is declined, meaning we can't accommodate to that when we have a lot of air pollution. And you might think, well, that's a funny connection. How can the heart's ability to change its heart rate be impacted by something you breathe into your lungs? And it gets even more complicated than that because the pollution gets into your lungs, then it gets into your bloodstream, and then it actually goes to the part that controls your heart rate, which is not your heart. It's actually your brain. And so your brain is impacted by air pollution that changes how your heart reacts. And so when we talk about air pollution, it's not just the lungs, it is your entire body. It is everywhere in your body that can be impacted by air quality.
Yeah. Which was actually what I was going to ask you next is just how much is the human body affected by air pollution? And I think, yeah, that was covered. But you had also spoken, and in a lot of your research, written about how vulnerable populations and people living in informal housing are more obviously at risk compared to others, and such populations are also more at risk to climate changes and the impact of climate changes. So, how are they more vulnerable? How are they affected more?
Yeah, so there are a couple of different answers to that question. We absolutely know that there are very specific vulnerable populations. There are people who are medically vulnerable, people who have diseases already. They have lung cancer, they have COPD or cardiovascular disease, they're elderly, they are a child who breathes a lot more per body weight. And so we know that there are certain populations, just as the nature of their kind of biological being, that they are vulnerable or more susceptible to air pollution. But at the same time, there's also people who are vulnerable because they are in closer proximity to the most polluting places. So we're talking about often the urban poor in the United States. We often have racial minorities who are more literally closer to the sources of air pollution that are often ignored by government regulators. And so there are two issues here. One is that there are people who are biologically more vulnerable or susceptible. Then there are some who are socially more vulnerable and susceptible because of their proximity to these sources. And it's very much an issue of justice. We know that as a society becomes modernized and we demand having our cappuccinos and our fancy cars and all of the wonderful things that come with a comfortable life. That comes at a cost that very often requires us to have polluting industries that support those things. So factories that produce the paper cups that I drink my cappuccino from, for example. And then we have waste products, for example. We need landfills. All that material we generate, we have to put it somewhere when we're done with it. Uh, and too often, it's the world's poor that are the ones that have to deal with both the factories that are producing these goods and the landfills that receive these goods after they've been used. And so we have a double-edged sword here. One is that there are certain populations who are biologically more vulnerable because of their age, because of their health status, but then there are those who are socially more vulnerable because they are in closer proximity to these things. The latter, has an additional complication in that very often government regulators don't measure air quality where the most vulnerable populations are. We just don't have we have limited resources to measure air quality. In the United States, for example, we use the United States Environmental Protection Agency. That's our agency to measure air pollution across the United States. They have a limited budget, and these monitors that measure air pollution are very, very expensive, and so they simply can't put them everywhere. And they make decisions on where they should physically place these monitors. And very often, it's not in the places of the most vulnerability. It's not the places where the pollution is the worst. It's not the places where the people are the sickest. It's often in regional locations that aren't impacted by any industry, and they're meant to look at kind of a big picture outcome of where air quality is in a given region. And so we've got really three factors at play here: people who are biologically susceptible, people who are socially susceptible, and the lack of data from those places where we see the most susceptible populations living.
Right. So, if we could now zoom in a bit on India, because air pollution is a huge thing, especially in the winter months here. So, one of the most obvious questions is, do episodic events like crop burning or bursting firecrackers cause increased aerosols or change the air around us?
Yeah, so I've been to India a number of times. Most recently, about a year and a half ago, where I was able to visit Ahmedabad and Kolkata and Delhi and Mumbai, uh, talking about air quality for the United States State Department. And I've published a number of papers across India for different projects looking at air quality. And India is a very complicated situation. There really are multiple layers of why air quality is poor, and it depends on the region of India that you're talking about. So let's start in the north. If we talk about northern India, we're talking about, say the capital region where you have rapid development. You often have high emitting vehicles driving around, lots of traffic. You have lots of industry that's grown up to support the growth of the nation. And that clearly impacts regional urban air quality around New Delhi, for example. Uh, but you also have this confounding problem from agricultural burning in the extreme northwest, both in India and Pakistan, because air quality does not know any boundaries. It does not restrict itself to a particular geographic boundary. It does not have a passport. It goes wherever it wants to go. Uh, and so the northern part of India, really across the entirety of across the entire Indo-Gangetic plain, is impacted by agricultural signal that happens typically in the fall and into the winter, but also enhanced by urban emissions from a rapidly developing major megacity. And so that's a complicated problem to solve because it involves both human activities in Delhi, for example, itself, people driving around and leaning on industries that are polluting, but also this kind of regional event that happens every fall, winter, with the removal of agricultural crop burning and stubble. Uh, Other parts of India have different issues. We see in, say, more, say, like Mumbai region, that's almost entirely urban emissions because it's on the coast and it does get a fairly nice coastal sea breeze with relatively clean air, although it's not pristine. You do get some air coming across the Gulf, uh, but most of the issues in the southern part of India, for example, are locally generated. They're generally not coming from the north. I know that there are some who think that there is a big plume of stuff coming down from the crop burning region. That generally is not true. When we look at where the wind blows, it really does blow from west to east, maybe a little bit southern, but for the most part, it's pretty rare to get that impact in a place like Mumbai. Uh, and so the issues in places like Mumbai are largely locally driven. They are the local factories, the local cars and trucks and traffic jams that happen in those regions. And so it is a different circumstance that you have to solve. And New Delhi has a much more complicated problem because they have that development and that kind of urban infrastructure that contributes to air quality, but they also have an agricultural burning problem too. That is kind of unique to the northern part of India. Yeah, there are always exceptions. There are strange weather events that might happen to bring smoke down from the north once in a while, but at large, on the whole, I should say, there is probably limited impact to the majority of India from those crop burning regions. The eastern part of India is also another issue because they have both development and urban growth, but also they do have some agricultural emissions that come from central India and the materials that might come from the Mumbai urban area. As it traverses across India, it's going to change. And as I said earlier, sometimes even gases that are released from combustion, or for example, will form particles, and those particles form as they travel across, and they impact the eastern part of India. And so it's a really complicated problem. To me, the first place you start is you start with good data. You start to understand what your problem is. Nobody tries to solve a problem unless you know the facts. And those facts have to be objective and based in science and based on best practices that we have. India has a fairly sophisticated network, but it's an undersized network for a country of that size, particularly for a place that's so complicated in terms of its air quality. It's one of those things that if I had a magic wand, I would double or probably quadruple the size of the monitoring network across India to get a better understanding of where air quality is the worst and why. And once you know that, then you can start making informed policy decisions to make it better.
Yeah, which kind of beautifully brings me into the next segment where I was going to talk about solutions and policy interventions. And in India, a lot of technological interventions have happened in like cloud seeding or smog towers, but these are also very cost intensive and probably not very scalable. So, kind of two questions here. One, are these kinds of solutions actually effective? And two, for the kind of complexity that the different regions in India pose. And the fact that we have local contributors and regional contributors, what would an ideal policy look like for a country like ours?
Yeah. So let's start with some of the technologies that are out there. So I know in Delhi there's been a number of initiatives looking at smog towers, these giant industrial factories that have big giant fans and filters that are meant to inspire air and grab the particles and release the cleaned air. Uh, if you ask me, do they work? Yes, they work if you live within, say, 10 meters of them. If you live on that block next to it, the big giant industrial factory, sure, they probably do improve your ambient air quality and probably indoor air quality too. Uh, but do they work at the city scale? I mean, absolutely not. Not unless you're going to spend hundreds of billions of dollars putting them on every block. It's probably not something that's going to be impactful for such a large urban environment. You just simply can't do that. It's unscalable. It's not something that would make any sense financially. Scientifically, it doesn't make much sense either because there are a lot easier ways to solve this problem. It doesn't mean that the ways are easy, but the ways are easier than smog towers on every block. Um, Other technologies, cloud seeding. Cloud seeding is interesting, but we don't know much about it. Cloud seeding is this idea that you can put gases and particles in the atmosphere. I mentioned earlier ammonium sulfate. You can introduce this material in the atmosphere and it can form clouds, which induces rain. And rain will both nourish the soil in places that are arid, but also it will often wash out a lot of the air pollution when it does rain. Uh, that is something that is potentially risky and it is potentially exciting too. It could be a really great solution,
Yeah.
but we don't know enough about it. It's too novel. The existing cloud seeding studies that have been proposed or conducted are pretty small in scale. And so I wouldn't go out and invest in cloud seeding technology just yet, not until the science can report on it. And unfortunately, this is a common thread you see in science is that we're slow and methodical and we take our time. Science wants to get the story right. And it takes time to get there. And we're not, and to my perspective, we're not there yet. So how does a country like India deal with complicated air pollution problems? Well, first you start at home. There are obviously important geopolitics involved here too. I'm not going to really opine too much on that because some of the air pollution problems do come from other countries for sure. But I would venture that at least a lion's share of the air pollution problems are homegrown, that they are formed within the borders of India that are potentially under their control. And so we can sort of dissect this one at a time here. Uh, First, as I mentioned, the most important thing that we can have to start with effective policies is providing better and more data. Empowering the regional monitoring authorities. I know it's distributed to the different states with resources to make the measurements that they need and make those measurements public. And I can't emphasize enough how important that data is when it's made public. And we know that sometimes when politics are involved, and not making any accusations, but sometimes when politics are involved, people will downplay data or they'll manipulate data if it's not public. And so having that scrutiny from the public, even the untrained public, has value to the public. And so it's important to make sure that that data is public and available and can be scrutinized by the public, but also by scientists who know the science well. And so that if I were to come in with my equipment, for example, as a researcher, and I could say, look, the Maharashtra monitoring station is exactly right, or it's 20% too low, or 50% too low. Or in some cases, you might find some places that are 99% too low. And we saw that happen in China in the late 1990s and early 2000s, where they were underreporting data all the time. And it took public dissemination of data to correct the country of China. And now China has outstanding monitoring, and they've done a really great job at controlling inequality. And so so once you've got a monitoring platform or a data platform established and the data is good, you can start to understand where air quality is the worst and why it's happening. And so there has to be an acknowledgement when it comes to policymakers that any kind of change generally has incurs a cost. There is a real cost to putting an emissions control system on a factory, or catalytic converter systems on cars, or asking farmers, or maybe not just asking, but requiring farmers to not burn their crop stubble. It's not that they can do something with their crop stubble. Right now, most of the crop stubble is just piled and burned. They might have to find another alternative for it. Is it something that can be plowed under? Can it be collected and processed in a factory into another material or good? Can it be recycled in some way, shape, or form, or composted? Those cost money to do. And so there is a real cost to making these interventions and mitigations. Uh, but you can't really determine where you should spend your dollars or rupees until you know what the most impactful problem is. I bet in a place like Delhi, you're going to want to spend, in the northern part of India, you're going to want to spend some effort controlling crop stubble burning that occurs each winter. And earlier you mentioned about holidays like Diwali and the contribution of things like fireworks. Yes, they definitely impact air quality, but they impact air quality for a few days, and that's about it. And so in the United States, we have another holiday in which firecrackers are very commonly used, the 4th of July. And we do see degraded air quality all the time on July 4th and July 5th. That's not surprising to us. But for the most part, the impact to our society is pretty small because it happens one day a year, a couple of days a year, something like that, similar to Diwali. You have structural problems in India. You burn crop stubble for months, and that impacts New Delhi for months. You have super emitting vehicles driving on the road. I think of places like Kolkata that use super polluting diesel engines in taxis, for example. Those kinds of things are very, very old fashioned and antiquated. And there's far better technologies out there that would result in much better air quality. And so that requires policymakers who are willing to make an argument and be bold. And yeah, there's a cost and a risk to doing that, but there's also a benefit. The hard sell is that benefit doesn't happen for months to years from now, when people are not getting sick and they're not dying and they're going to school and they're not calling out sick for work. Uh, those benefits are economic benefits that are realized well after you've spent the millions of dollars today to improve air quality. And so it's a hard sell, and it's also a marathon. It's not a sprint. We have to know recognize that these kinds of impacts take time. If the United States is an example, and I'm not saying it is the best example, but it took us 40 or 50 years to get to where we are. If we hadn't taken those difficult steps starting in the 1970s, we would still be in super polluted conditions with 100,000 people a year dying from air pollution. Now we're probably under 30,000 people a year dying from air pollution because conditions are so much better here. Because politicians were willing to take that first step along that marathon of improving air quality.
Right. Thanks, Richard. So that was the end of my the main questions, but we thought we could just do a quick kind of rapid five,
Sure.
summing up the entire interview. So, what are aerosols and how do they affect our health and the climate?
No, they're all the particles and gases in the atmosphere floating around. Sometimes you can see them and sometimes you can't. They all cause us to get sick and they drive climate change.
How do aerosols affect both global warming and global cooling?
Aerosols sometimes reflect sunlight. They send it back out of the earth, but other kinds of aerosols actually absorb sunlight, and so they can make it warmer.
Right. What is the biggest challenge in protecting people's health when it comes to aerosols and air pollution?
Recognizing that aerosols are impactful to health. People don't realize that these are important to us and that they do cause people to get sick. And so education is important here.
How connected are air pollution and aerosols with extreme weather events?
The connection is probably not the strongest because we don't know a lot about that connection. There probably is one, but we don't have good scientific evidence to say that aerosols are driving these extreme weather events. They clearly are associated with each other, but it's still pretty uncertain.
Right. If you had the chance to right now implement a policy that would help reduce aerosols or tackle it, what would it be?
In a place like India, I would restrict crop burning in northern India, and I would improve cars and vehicle emission controls as well.
That's it. Thank you so much, Richard, for your time. If you like this episode, subscribe to us wherever you get your podcasts.